Hey, can you guys hear me okay?
Yep.
Outstanding. Standing out. All right, so I think that, let's see, what is it that I think? I don't know, I think a lot of things. But I think this is one of the things that we were talking about yesterday near the end of the class. And I think that we've got a fairly good understanding both intuitively and if you had to, I think you could derive this equation. The reason I say that is because one time I tried to derive it just to prove to myself that I could, and I could figure it out. And if I can figure it out, you guys can figure it out because I know we're all good at math. All right. So we know that we want to model our cutting system, our manufacturing system, so that we can predict how it will behave, both to figure out what parts what surface features we'll be able to put on parts through using the process. And also we want to be able to know, are the process variables that I've chosen, are the PVs that I've chosen going to cause the part to explode or cause the tool to explode? Right, so I want to now go through a bunch of different models for cutting. Oh, so before I go too far though, there is no quiz this week. So there's no quiz this week. We will have a quiz next week, which covers the stuff that we're talking about this week and the stuff that we're talking about next week. So before you think I forgot to post the quiz, there is no quiz this week. All right, so quiz this week. All right, so let me quickly turn off the screen share and have you guys. All right. So what do we already know about our cutting system, whether it's turning or milling? What do we already know about it that we could express as a mathematical model?
Like speed.
So we know that the feed speed, depth of cut are important. We know that the simpler model to start with would be the one where we're doing a turning operation. And we know that we can model surface roughness. And if we want to model surface roughness, what do we need to know about?
Tool radius.
We need to know the tool radius. And we need to know the feed, right? And as long as we get the feed in the correct units, we can figure out something about that surface roughness on the turn part. So we can make a model and predict that. What else do we know about our turning let's just focus on turning operations right now. But I will tell you right now that everything we learn and figure out for a turning operation is exactly the same in a milling operation as long as you get the axes oriented in the right direction. So the chip forming on the edge of a turning tool is the same as the chip forming on the edge of a milling tool. It's just they're not going the same direction relative to where the operator is standing. So what do we know from physics about our turning and cutting operations? What kind of models could we develop that would predict something about the process?
Like, what do you mean by like what kinds of models? Like, like software or like physical or?
So as engineers, I mean, we could make a model like this, right? So we could make a physical model so that we can look at something. But the models that are more interesting to us as engineers typically are mathematical models, where we can create some equations or figure out some pattern or read off of a graph and predict a behavior of some kind. And so with turning, we can predict surface roughness. Then we can also predict something about the geometry, right? If we know the depth of cut, which is this distance, we know the depth of cut, then we can predict what the finished diameter is going to be, right? As long as we know what the original diameter is. So we know the original diameter and we know the depth of cut. We can predict the finished diameter. So we can predict something about the geometry for our turning operation pretty easily. So here's our model. And remember, dF equals dO minus what? 2 DOC. Is that correct? I really hate to write equations when I'm doing a lecture because sometimes I screw up. So if I ask you if that's correct, it's not rhetorical.
Yes, it is.
Okay, good. All right, so we have models then for our turning that can predict the geometry of the finished part. We said we also might want to predict the cutting forces so that our tool doesn't explode, right? So what do we know about force?
Equals mass times acceleration.
All right, F equals ma. Can we know what the mass is? I've actually never tried to derive it from this direction, but.
Well, doesn't the CNC machine tell us like how much mass is going to be removed?
No, not by itself. If we want to know how much mass is going to be removed, we have to figure that out. But let's just think beyond F equals ma. Do we know how much power it's going to take? What's power equal?
Force times velocity.
Power equals force.
Oh, no, not velocity. Power to cut equals force times surface feet per minute. So that's your feed
Force
speed.
times velocity. The velocity that we care about is the velocity of the cutting edge moving through the workpiece material, which is the surface speed. So yeah, so force times velocity is power. Now, so we know the power at the cutting edge of our tool. The power that's going to that cutting edge equals the cutting force times the velocity, where the velocity is the surface speed that comes from the rotation of the spindle. So we know that. So that's pretty cool. What will impact how much power it takes to cut material? And we talked about that, I think, a week ago today.
Tool sharpness?
The sharpness of the tool. We call that W. What else will affect how much power it takes to make the cut?
Hardness of the material you're cutting.
There's a material property And it's not just the hardness, although the hardness probably correlates with this property, but we call it the specific energy for cutting. And so, or specific power for cutting if we're calculating power. And so we'll call that KP. And so W actually stands for tool wear factor. Which is really just a measure of how sharp is the tool. KP is material specific. It's material specific power. Material specific power factor. What else will it depend on? So it'll also depend on our material removal rate, which we call Q. And remember, our material removal rate is the volumetric rate at which we take material off the workpiece. And when they figured all of this out, they realized that, and so how did somebody figure all this out? First off, they had a theory, right? So somebody had a theory that it would depend on how much material we're removing, something about what kind of material it is, and how sharp the tool is. So that was how the theory was developed. They said that. And when they went to find out the something about the material and how sharp the, when they went to figure this out, they developed a series of experiments. And they went through and they used all the same material and they varied the sharpness of the tool. And they saw how the results came out. And then they varied the material removal rate, keeping the tool the same and the material the same, and they saw how the results came out. And then they did a full matrix of these different experiments, and they figured out that their model, in the model said that the power of cutting equals Q times W times KP. So the initial model says this. When they finished, they realized that it was close, but it varied depending on how fast the feed rate was. And so when we developed a model and we find out that our model doesn't behave exactly the way we think it should, what do?
Start over?
No, we don't want to start over. We spend all that time doing all the experiments.
Yeah, test more variables.
We say there's got to be another variable that's impacting this that we hadn't thought of, right? They figured out it was the feed rate by itself. And so what they did is they did another experiment where they varied the feed rate, and they came up with the feed rate factor. So let me just write it down. So KP QWC. And so if we know Q, how do we find out Q?
Material removal rate.
We choose Q because that's something that we have control over. Q is going to depend on the feed, the depth of cut, and maybe the RPM depending on what your units for feed are, right? Okay, so we get to choose Q. How do we find out the values for KP, W, and C? All right, so one way we could do it is we could do our own experiment. Do you want to do an experiment every time you need to know this?
No.
No.
I want to have a good
I
model.
think somebody else has already done the experiment.
Yes.
If you think somebody else may actually, whether you think somebody else has done the experiment or not, you should go look to find out if somebody else has done the experiment. When I first started graduate school, my advisor told me something that he thought it was kind of a funny joke, and he's like, what you're going to learn is that a few years doing research in the lab could save you a few days doing research in the library. And so he's trying to point out that you should do the research in the library first to find out if somebody else has already done the research you want to do and already knew the answer, so you can just go look up the answer. Now that we have the internet, it really is only a few hours of research on Google, or maybe a few minutes of research on Google. But you can look at the Machinery's Handbook. The Machinery's Handbook has a whole section it's at page 1024, I think. So 1054. Their machining power. And you can look up things like KP. Look, it's in there. Now, I could have required this as a textbook for the class. And I could have made you all pay $115 to get one of these so that this week you could look up the factors that you need from this in order to answer the quiz questions actually next week, because that quiz is next week. But I decided not to make this be required as a textbook for the class, although you maybe want to get one. Instead, I need to share the screen now. I'm going to share this screen. Instead of making it be required reading for the class, I made sure that the library, the one at WPI, has the electronic version that you guys can access. So WPI library. Click the link. Type machineries. Actually, I've proven that you don't have to spell it correctly, but Machinery's Handbook, search. And you'll note if you scroll down here, there are several different editions of the Machinery's Handbook available to you online. Oh, look, the 31st edition finally came out. I usually use the 28th edition. It doesn't matter to me which edition you use. Let's see, available online. This should open right up. If you are at home and not on a computer connected to the WPI network, as long as you go to the library's webpage first and search for it, when you get to clicking the link here to bring you to this page, it should give you the opportunity to log in with your WPI username and password. If that does not work, please contact the library help desk. I can't fix it. But here we're in our Machinery's Handbook table of contents. We want to understand the power that it takes to do a cutting operation. I think that it's in the machining operations section. Look at that. Cutting speeds and feeds. So there's some reference tables here that we're not going to use in this class and the feeds and speeds part of it, because you did the feeds and speeds part of your lab exercise where you saw how to look up the feeds and speeds for the tools that we use here on campus. But estimating speeds and machining power. This looks pretty good. So we want, so there's different kinds of cutting operations. And so there's some information here about planing and shaping. We're not doing planing and shaping, so we can go past that. There's some information here about saw cutting. We're not doing that, so we're going to go past that section. And estimated machining power. Estimating machining power. So when we get to this section, I recommend reading these paragraphs because it'll explain the units for KP and things like that. But then you come down here and for different materials, it shows the experiments of, shows the results of those experiments for KP, and note that there's a KP value for inch units and there's a KP value for metric units. It'll tell you what those units are up here. If you scroll down, keep scrolling, there's a lot of different materials that they have tables for. Once you get done with that, you can, this window keeps popping. Anyway. More KP values. Oh, here's feed factors. And so you'll see that these feed factors, depending on what your feed rate is, the feed factors go from about 0.98 to about 1.6. Tool wear factors is going to depend on what type of operation you're doing. But tool wear factors are anywhere from about 1 to 1.6. If you don't know what the tool wear factor is because nobody told you, use a tool wear factor of 1. If you go to validate your result and you find out you're wrong, it'll be something like the tool wear factor being off. The feed factor you can figure out from the table here because you know what your feed rate is. You choose that. Let's see, and then in material removal rate, they got some formulas here for helping you figure out material removal rate, but you can really figure out material removal rate just by knowing what the units are and knowing about your operation. Now, there's a factor E here, machine tool efficiency, that was not in our model that we drew on the board. One of the things that you find out is it's very easy to monitor the power that's going to the spindle of the machine tool. You can hook up actually all of our machine tools when you're in lab. If you're in lab, when you run the machine, you'll see that there's a power meter that goes like this as the machine's cutting. That is measuring how much current is being used by the spindle at that moment. So it's very easy to measure the power that goes to the spindle. Not all of the power that goes to the spindle gets to the cutting edge of the tool. Why?
Friction.
There's friction, there's losses in the system there. And so depending on the type of drive system that your machine has, there are some machine efficiency factors here. If you have measured the power at the spindle and you want to know what the power at the tool is, you can use one of these efficiency factors. If you have estimated the power at the tool and you want to know, does my spindle motor have enough power to make that cut, you can go back the other direction. And so for the sake of the class, we will either tell you the type of drive system that the machine has, or we'll tell you what the tool efficiency factor is if you need to do that part of the calculation. So based on the information in the machinery's handbook, or the online version of it, you can now estimate the power for cutting as long as you know what material you're cutting, and as long as you have already selected the material removal rate, the feed, speed, and depth of cut. And so this is why I say feed, speed, depth of cut are the primary, the most important process variables in CNC milling and turning. However, they're not the only ones that are important.
Could you say that again? So as long as we have
So if you
material,
have chosen a feed, speed, and depth of cut,
yep, and the
and
material,
you know what the workpiece material is, you can estimate the power for cutting, because you can go to the machinery's handbook and you can look up the KP value, the W, and the C, because you know the feed, speed, depth of cut. And you can calculate material removal rate. If you know what type of machine tool drive system you have, you can estimate how much of this power for cutting is, how much more power is required at the motor, because you're going to lose from the motor to the cutting tool, to see, does the motor on my machine tool have enough power to make the cut that I want to make. It won't tell you, is the tool about to explode, but it will let you know, is the motor going to stall before I get finished making my cut. So you can estimate that using the information that people found experimentally and published in the Machinery's Handbook. But let's see if there's any other way we can find out about those cutting forces and thus the power. So I want to draw my turning model again. We're going to ignore the surface roughness part of this for right now, just focus on the geometry. So as the tool moves as the tool feeds in this direction, the part rotates in this direction. I'm not sharing the screen, right? So you guys can see the whiteboard?
Yep.
Okay,
Yeah.
good. Just making sure. Sometimes I go on for like 10 minutes and then people say, what are you talking about? We can't see what you're pointing at. All right, so as we move across like this, for each revolution of the workpiece, the tool is moved like this, right? And so after one revolution, it'll look like that. And there's some distance here that is the thickness of the chip. If I hold up my model here, let's see if I get the same orientation. This is pretty much the same orientation. So the distance I'm talking about is, you know, it'd be really cool is a piece of tape. I was going to draw on my thing, but I have learned that drawing on it doesn't work very well. All right. So now you get some contrast. All right, so the distance that the tool moves in one revolution, the tool moves in this direction in one revolution, is from the tip of the pen to where the tape is. That's this distance here, which is the uncut chip thickness. We call that T1, it's uncut chip thickness. All right, so what is T1 equal to?
the radius?
No. No, it's the distance. So the tool is moving this direction. The uncut chip thickness is measured perpendicular to the cutting edge of the tool. And so there's an angle here. From the cutting edge of the tool. So if the tool was not at this angle here, the uncut chip thickness would equal the feed rate. As long as you have the right units, right?
Right.
All right, but since we have that angle, it doesn't equal the feed rate. It equals the feed times cosine of the angle. And we call that the side edge cutting angle. Don't ask me why we don't have a better variable name for side edge cutting angle other than SECA, but all the literature calls it the side edge cutting angle, and that's how they report it. So T1 equals the feed times the cosine of the side edge cutting angle. If the side edge cutting angle is 0, what's the cosine of 0?
1.
1. So when the side edge cutting angle is 0, the T1 equals the feed rate. It does not equal the depth of cut. This is a mistake people often make, so I'm reminding you that T1 equals feed times the cosine of side edge cutting angle and does not equal the depth of cut. We need to know the depth of cut when we're figuring out material removal rate, but not when we're figuring out T1. Okay, so that's kind of cool. It'll tell you the uncut chip thickness. It tells you how thick the material is that you're removing as you do that. Let's look at that cutting operation as it happens. Go back to the screen share. Share this one. And you can see the screen now?
Yep.
Oh, this one has loud music. I'll turn that off. We don't need the music. All right, so here's our cutting tool. Here's the work piece that's about to be cut. This top face of the cutting tool there that we're looking at, we call that the rake face. And so the chip forms and it slides along that rake face of the tool. We're going to change orientation here in a second. There's the chip forming and sliding across the rake face of the tool. Now, if we're looking straight down the edge of the cutting tool, so we're looking in, there's the button. So we're looking in this orientation, straight down the edge of the cutting tool. The chip forms, slides across that rake face, and we can draw what it looks like here. So here's our cutting tool. Here's the uncut chip thickness, which remember is the feed times the cosine of the side edge cutting angle. And here's the chip as it slides across the rake face. Now, in our video there, you see that the chip doesn't slide flat across there, right? It curls up. The reason it curls up is because this tool has this little divot here. Well, actually, one of the reasons it curls up is because the material is Delrin, and the Delrin chips always curl up like that. But the reason it also curls up because this has this little divot here, so that rake face is not flat. That change in shape of the rake face is intended for more brittle materials to cause the chip to curl back and break, so you don't end up with a long string ribbony like chip. Why would we not want to have a long stringy chip in our cutting operation?
Can get caught.
It'll get wrapped around stuff, caught on stuff, especially if you're using a machine tool that doesn't have an interlock on the door. You're tempted to just reach in and pull it out of the way. What happens if you reach in and try to pull it out of the way, or what might happen?
You might have to go to the ER.
Yeah, you might lose your hand. You might lose more than your hand. Because if the chip does, as you're trying to pull it away, it does get caught on something, it's going to pull you into the machine instead of the other way around. So one of the reasons we like the CNC machine tools with the interlocks on the doors, no matter how tempted you are to pull it away, you can't, because if you open the door, the machine stops. All right, so let's look at our model again now. So based on what we see there, we can draw this model. And I think, go ahead. Yeah, I zoomed out a little bit here on our model. All right, so we've got, remember, our final diameter, original diameter, our depth of cut there, our chip thickness, our uncut chip thickness, feed speed. Okay. The tool here, if we were to tip the tool in a different orientation, let's see, annotate. I think I can do this. Draw a line. All right, so right now our tool is oriented like this, and it's perpendicular to the direction of the workpiece material coming towards the tool. So the angle of the tool here, so that our perpendicular angle, if we were to tip the tool like this, then the chip would flow along the tool edge there again, right? So the chip is still going to flow along that tool edge. That angle, whether we tip it down like I showed here, or we tip it up like this, that angle is called the rake angle. And so if I turn off my screen share for a second. So here, the rake angle in this orientation is how much the tool is tipped. Rake angle. Yeah, how much the tool is tipped like this or like this, relative to the motion of the workpiece. So that's the rake angle. A cool thing that we can figure out from geometry, screen share back on. A cool thing that we can figure out from the geometry of the cut here in our model, next slide, is that right here, as the tool's cutting across the material, it stops being workpiece right here and starts becoming chip. As the chip slides along here, this always lines up in a plane that cuts through the chip. The angle that that plane makes depends on the ratio of the uncut chip thickness, the ratio of the uncut chip thickness, and the rake angle. And so you can actually prove this with the geometry. I won't ask you to do that. Once I asked an M1800 class to prove that that was true based on the geometry, and as extra credit, and about 15 people submitted the extra credit assignment, and I had proved it to myself to make sure that I could do the proof before I asked the students to prove it, and not all of them submitted the same solution that I had come up with, and so then I had to check all of their solutions to see if theirs was correct also. So I won't ask you to do that. There's more than one way to prove it's true. All right, so there's a relationship between the shear angle, the uncut chip thickness, and the chip thickness. Why isn't the uncut chip thickness equal to the chip thickness always?
Internal stresses in the material.
Right, so when we go through this shearing that happens in the shear plane, when we go through that, it deforms the material. It changes the grains of the material. They change shape, they change orientation. And so we're putting energy into this chip plane here, and it distorts the material and it comes out at different sides. How do we know the uncut chip thickness?
It's the feed times the cosine side end cutting angle.
How do we know what the chip thickness is?
Chip thick.
Yeah, no, you answered the first question correctly. Second question is, how do we know what the chip thickness is? There's a hint in your kit.
Do you not just have to measure it with like a caliper?
Yeah, you pick the chips up off the bottom of the machine tool. And so if you happen to have your kit with you, if you notice there's 3 little bags with chips in them, there's a shiny side on each chip. The shiny side is the side that rubbed against the rake face of the tool. So when you measure that chip thickness, and that's one of the things that we're going to do for our little lab report is measure those chip thicknesses. When you measure that chip thickness, you want to measure from the shiny side to the side opposite the shiny side. And you can do that with your calipers to measure that chip thickness. So if you know what the rake angle is, and you know what the feed rate was and the side edge cutting angle was, you can determine what the shear plane must have been. That's kind of cool, I guess. Why do we care what the shear plane was? What the angle of the shear plane was? Well, first off, let's just look at a more simplified version of this model. So we've got our rake face, our tool here. There's the shear plane. Here's our chip. Here's our workpiece. If we look at this, would you agree?
Could you upload these diagrams for us?
Yeah. Actually, there's I'll make a link to these slides for you in the syllabus document there. Actually, that's one other thing that I never went over in class, but I did add the rest of the syllabus pages here. So in here, so if you click on this, you get to the rest of the syllabus page. Next slide. I cut out the stuff about late submissions. There's our grading expectations, all that stuff. Schedule. So this force here is what the tool pushes on the workpiece with. So the tool pushes on the workpiece pushes back on the tool because it's not accelerating across the room, right? So there's a force here. The nice thing about every force is we can break it up into orthogonal components. We can say that this FC here, which we call FC for cutting force, lines up with the direction that the tool is moving through the workpiece. And there's an FT that lines up with perpendicular to the direction the tool is moving through the workpiece. And those two add together to equal the resultant force, which is the total force between the tool and the workpiece.
It looks like that the shear plane or shear angle, it looks like that it's perpendicular or mirrored to the
coincidence in this particular diagram.
Oh, okay, never mind.
That angle could be anything depending on how you. It's hard to draw this without making it look like two of the planes are orthogonal, but they're not. But we could also take this resultant force and we could align it with the force that lines up in the shear plane. So this force that lines up in the shear plane is what causes that deformation, right? That deformation is caused because there's a force pushing in that direction, and then there's a force normal to the shear plane. So we could break that resultant force up that way. But remember, our chip is sliding on the rake face of the tool also, right? So we know that as the chip slides on the rake face of the tool, it's trying to push the tool away. And so we know that there's a force that lines up with the rake face of the tool, and there's a force normal to that that also have to add together to equal P, because the system is stable. It's not dynamic. It's not accelerating. So we know that all three of these force systems equal P. And if we know this shear angle, and we can figure out the shear angle by knowing what the uncut chip thickness and chip thickness are, if we know what that shear angle is, and we know what the rake angle is, we can actually convert from one coordinate system to the other just with geometry and trigonometry. A cool thing here, though, is mu is the friction coefficient, right? The friction coefficient between the rake face and the chip equals the friction force over the normal force, equals the tangent of the angle between that normal force and the resultant force. We also can figure out, if we know that the cutting force and the thrust force, this cutting force and this thrust force, are related to the friction and normal forces because of the rake angle, because the friction force is aligned with that rake angle. And so we can make that conversion. And there's this guy named Merchant that figured out experimentally that the shear angle is also related to the friction angle and the rake angle. And so we can convert from one system to another. Now, why might we know what the cutting force is? If we're doing an experiment in our machine, why would we know what the cutting force is? We can estimate what the cutting force is with our machinery's handbook, right? We have our machinery's handbook, we can estimate what the cutting force is. If we're standing in front of the machine tool, we could measure the power that's going to the spindle motor, and we could know what that cutting force is. So we could experimentally find these out. We also could put a force meter in the machine tool in an experiment, and we could find out the cutting force and the thrust force. How could we know what the shear force is? Could we measure that directly? Maybe with strain gauges embedded in the material that we're cutting, but probably not. It'd be really hard to measure the shear force directly. I think we could probably measure the friction force directly if we wanted to, but it's really easy to measure the cutting force and the thrust force. So if we're made some of these measurements, now why do we care about any of this? Besides the fact it's on next week's quiz. So why do we care about any of it? See, this is why this lecture goes way better if you're in the classroom.
Is it so you know when your tool will break based on the
See,
forces?
this lecture goes way better in the classroom because this is the day that I bring a bag of candy to the class. And if you answer my question, I throw a piece of candy at you.
Can you hear me?
Yeah.
Okay. Because when you have to do this yourselves, it's going to be nice to know how to do it, because it's going to be hard when you're not with us to walk us through it.
Well, there is that, so it'll help you with the quiz. But why did people even figure it out in the first place?
So
So they could,
Because
Doug,
hundreds of millions of dollars have been spent figuring this out.
so they can tell when the tools are going to break based on the forces on them?
It's so that you can predict when to change the tool, so that you can figure out how fast can I go. Why do I want to go faster?
because time is money.
time is money as long as you have a customer to buy the parts. It's to almost all of the rigorous math that I just presented, all the experiments and the stuff that were done figuring this stuff out was done in the 1930s and 40s. Why is that?
War.
Because we needed to figure out how to build airplanes and battleships faster. And so it was all about how fast can we go in order to get more chips in the bucket so that we can get more ships in the water, more airplanes in the air, more bombs dropping out of the airplanes. So we figured this stuff out in order to be able to do stuff faster. The kind of research that's going on right now is, and there's still people doing research in this area, but the kind of research that we're doing right now is trying to ask, how small of a chip can we make? So how small can that uncut chip thickness be before you can't possibly make a chip anymore? Because we're trying to do micro machining and things like that. So there's still research going on in these areas, but the stuff that we just went through, that's been well understood for 50, 60 years. And we figured it out because we were trying to make weapons. All right. And I did adjust the schedule from what I had originally intended to do. That's one of the reasons that the quiz is delayed next week. Next week on Monday, we're going to talk about stress, strain, and fixture design. We're going to continue talking about power and chips and chip formation on Wednesday in our lab lecture. We're going to actually go out and do part of the experiment at the machine tool on Wednesday next week. And Thursday, what are we doing on Thursday? Thursday next week, we're going to talk about functional design and tolerance selection. Oh, and we're going to use this again when we do tolerance selection. That's what I got. No quiz this week. I'm going to right now make a link. So the presentation I was using here is called Equations in ME 1800. I'm going to make the link to that right now. In this week's oh, that's a lot. You can't see the screen anymore, huh? You're just watching me type. I'll stick around for questions if anybody's got questions. I'll go ahead and stop the live feed.